Hi, my name is Bruce Bouquet, and I'm from the New Jersey Institute of Technology. Welcome to Numerical Methods, how to use computers to solve difficult math problems. In this podcast, we'll continue with our discussion of root-finding methods. Here we'll discuss Newton's method. All root-finding methods are used to find the approximate roots of nonlinear equations. These equations are often difficult or even possible to solve analytically for their roots, and so we need to use approximation methods. Earlier we discussed the bisection method. And Newton's method is really the same as finding tangent lines and finding where the tangent line crosses the x-axis. It's the same as linear approximation and finding where the linear approximation crosses the x-axis. So tangent lines, linear approximation, and Newton's method are really all very similar. Okay, here's the main idea. What we do is we write the equation as f of x equals 0, finding a root of the equation. Here's a function on the right, and we see it has a root over there. So we make a guess for the desired root. Sometimes there's more than one root of the equation, so we want to get an approximation for the root that's pretty close to the true root. We approximate the curve with the tangent line at our guess. So we're going to make a guess, say over here. We're going to draw the tangent line at that point, and we'll see where the tangent line crosses y equals 0, or the x-axis, and that's the next iterate. And then we go on again, find the y value at that point, the slope, and we continue on, and we repeat until the answer stops changing. And of course we have to check that our solution makes sense. So here's what we're doing at the point that we're guessing. We draw the tangent line. We see that the tangent line crosses the x-axis over here, and that would be our next iterate. How do we work through the details? Well, we want the tangent line to y equal f of x through our initial point, x naught, f of x naught. So we write the equation of that tangent line, the linearization, f of x naught plus the derivative f prime of x naught times x minus x naught. And we define x1 to be the point where that line crosses the x-axis. So we want L of x1 to equal 0. Plugging that in, L of x1, over here we just plug in x1 for x, and we solve it for x1, and we find that the new guess should equal the old guess minus the height of the old guess, the y value at the old guess, divided by how fast the curve is moving at that old guess. Okay, and in general, we would have the next iterate is equal to the old iterate minus the y value at the old iterate divided by the slope at the old iterate. Let's do an example. Suppose we want to approximate the cube root of 2. So we find an equation for which this is the answer, the obvious equation that we're going to use. There are many choices that are possible. Is x cubed minus 2. Because if you said x cubed minus 2 equals 0, you'll get the answer that x is equal to the cube root of 2. A reasonable starting guess? Well, we have to find one. We can note that f of 1 is 1 minus 2 is negative 1, and f of 2 is 8 minus 2 is 6. So there's a root between x equal 1 and x equal 2. And the function is continuous on that interval, so there is at least one solution on that interval. One can use the mean value theorem to show that there can only be at most one solution to x cubed minus 2 equals 0. So we'll start with x equal 1 because the y value at x equal 1 is closer to 0 than the y value at x equal 2. So what do? We are trying to solve x cubed minus 2 equals 0. F of x is x cubed minus 2. We need to find the first derivative. That's 3x squared. The general rule for our iteration scheme is x sub n plus 1 is xn minus f of xn divided by f prime of xn. And if we plug in our information up here, that becomes xn plus 1 is xn minus xn cubed minus 2 divided by 3xn squared. Okay, if our initial guess is equal to 1, x naught is 1. And we already saw f of x naught was negative 1. F prime of x naught is clearly 3 from the 3x squared. And we plug in. We get the new value, x1, is equal to the old value, which was 1, minus f of x0, which was negative 1, divided by f prime of x0, which is 3. So we get 1 minus negative 1/3, or 4/3. and we can then see that the y value is no longer -1. Now the y value is close to 1/3. Okay, and the new x value is 4/3. So we do the whole process all over again. The new value, x2, is going to be the previous value, 4/3, minus 4/3 cubed minus 2 over 3 times 4/3 squared. And if we work through that algebra, we get 91 divided by 72, which gives us a y value of 0.02. So it appears that we're getting close to a root. If we do it one more time, we find x3 is 1.2599335 and more digits. And the y value there is about 6 times 10 to the minus fifth. So we see that the y values are getting very close to 0. We note that we started with y value of -1, then 1/3, then 0.02, then 0.0006, and the true answer is 1.259921. So we see that after 3 iterations, we are correct to 1, 2, 3, 4, 5 terms. We have 5 decimal places that are correct. Graphically, what did we just do? Well, we started at the point 1, -1, found the equation of the tangent line. We saw that the tangent line crosses the x-axis at x equals 4/3, and the y value over there is 10/27. Okay, so we find the y value, then we're going to find the tangent line at 4/3, 10/27, and then we get to our x2, right? Our x1 was 1, our x2 was x1 was 4/3, and x2 is 1.2639. Okay, now that was a nice example, but with the Newton's method, there are problems that can arise. So if we consider the equation 17 plus 8x squared minus x to the 4th equals 0, starting with an initial guess of x naught equal 1, then what happens is we draw the tangent line, we get a new x value, we plug in that new x value, and we find that tangent line, and it gets us right back to where we started. So we could have oscillation. That note, in this case, there are 2 roots that are shown. One is all the way here on the right, one is here on the left. And we're not starting very close to a root. If we start far away from the root, we might end up at another root, or we might end up very far away, or we might end up in this case where we just get oscillations going back and forth, and the method would not converge. There's also a problem since we are dividing by the derivative of f of x. If the derivative is 0 or near 0, we can have problems. Again, if we had chosen x equals 0, x naught equals 0 for the initial guess, in this case the 17 plus 8x squared minus x to the 4th equals 0 situation, then we have a tangent line that's horizontal. It never crosses the x-axis, so the method would not work in that case. Another example is where you have 1/4 x squared equals 0, so the derivative at the root, clearly x equals 0 is the solution, the derivative at the root is near 0, right? The derivative of 1/4 x squared is 1/2 x, and at x equals 0, the slope is 0. What happens is, well, we suppose we start with an initial guess of x0 equal 2, then the next iterate will give us x1 equal 1, the next iterate will be x2 equal 1/2, and the convergence is quite slow, starting at 2, then 1, then 1/2, and so on. So if the derivative either at your initial point or near your initial point is approximately 0, or at the root, if it's 0, then Newton's method can have problems. In the last case, where the derivative is 0 at the root, the convergence still works, the method still works, but the convergence is slow. Let's discuss error analysis for Newton's method. Suppose we have alpha being the exact root, then f of alpha is 0. We can expand f of x around the nth iterate. So we have f of x sub n plus alpha minus x sub n, f prime of x sub n, plus 1/2 alpha minus xn squared times the second derivative somewhere between alpha and xn, right? That's going to be the value at of f of alpha. That's just the Taylor series expansion with remainder of f of x around xn and using it to find f of alpha. But we know that alpha is the real root, so f of alpha is 0. So if we plug in f of alpha is 0 and we divide by f prime of xn, we get 0 over here on the left. We get alpha from this term. We get f of xn divided by f prime of xn. Over here we have minus minus, so that's from the plus. We have minus xn from this term. Okay, and we have the term on the right is divided also by f prime of xn. Now we can note that this expression in parentheses, that's how we got xn plus 1, the next iterate. So we get alpha minus xn plus 1 plus the third term over here. Okay, and so what we have, bringing the alpha minus xn plus 1 to the other side, that's equal to the error at the n plus of the n plus first iterate, alpha minus x sub n plus 1. That's the true value minus the x plus first iterate. So the error at the n plus first step is equal to this messy expression times the error at the nth iterate squared. So we find that the new error, the error at our new term, is equal to some expression dealing with the first and second derivatives of the function times the error at the nth term. Now, if your derivatives and second derivatives are not changing very quickly, this is roughly equal to a constant. So we have the error at the n plus first step is proportional to the square of the error at the nth step. That's called quadratic convergence. The new error is something times the square of the old error. So if we call capital M the maximum value of this messy expression in the region between alpha and xn, then what we want to have happen is that the new error should be smaller than the old error. So plugging that in, we get that the new error is less than or equal to m times the error at the nth step squared. And we want that to be less than the old error, dividing these last two sides by the previous error, the e sub n. We get m times e sub n should be less than 1, and thus we want the initial guess to be within 1 over big M of the root that we're looking for, and then the method should converge. Hopefully we'll have an initial guess that's even better than that. So some of the rules of thumb with Newton's method is that we want an initial guess close to the root. We don't want to have our initial guess where the derivative is near 0 or at a local minimum, and we want to have the derivative non-zero near the root and, of course, at the root. Some of the properties is that the convergence is fast. It's quadratic. When it works, it often works really beautifully. It finds one root, which may not be the closest root if you don't start close to the root that you want, or if the derivative is near 0 where you start, and it may not converge, as opposed to bisection, which has guaranteed convergence but much, much slower convergence. A moment of culture. There were once 3 prisoners of war who were told to dig ditches, and 2 of these prisoners of war were engineers and 1 was a mathematician. So naturally, as things would have it, the mathematician stood at the top of the ditch, and the 2 engineers were digging the ditch, and the mathematician was telling the engineers where they should dig, whether they should dig faster, slower, where they should put the dirt, and so forth. So one of the engineers said to the other engineer, "What's going on? Who does he think he is out there at the top of the hole telling us what to do?" And the other engineer said, "You know what? I'm going to go find out." So he goes out of the hole and says to the mathematicians, "How come we're doing all the work? We're digging. You're giving us all the orders. What makes you so important to be the boss?" The mathematician naturally says to the engineer, "Well, I have something that you probably never heard of. It's called brains. Let me show you what brains is." And he goes over to a tree, puts his hand on the tree, and says, "Hit my hand as hard as you can." And the guy winds up, and the engineer punches at the mathematician's hand, and the mathematician moves his hand away, and the engineer hits the tree, and his hand is all bloody and bruised. And naturally, the engineer goes sulking back into the hole. So then that engineer tells the other engineer where to dig, how fast to dig, where to put the dirt. And the other engineer that was back in the hole says, What's going on? I have the mathematician telling me what to do, and now I have you telling me what to do. And the other engineer with the bruised hand says, well, look, this has something to do with brains, which I happen to have and you happen to know nothing about. And let me show you what brains are. And he puts his good hand in front of his face and says, hit my hand as hard as you can. I'm Bruce Bouquet from the New Jersey Institute of Technology. Thanks for joining us, and may the power of math be with you.